In this video, we'll discuss what the momentum equation is and its application in fluid dynamics. Linear momentum equation for fluids can be developed using Newton's second law of motion. This states that sum of all forces must be equal to rate of change of momentum. Okay, so sum of the external forces in a control volume is F. That should be equal to rate of change of momentum, which is mass times velocity divided by t. Okay, so that means change of momentum is mass times velocity minus mass times velocity. So whatever mass times velocity here minus mass times velocity there divided by t. And we also know that force equals to mass times acceleration. So same thing, force equals to mass times acceleration. Acceleration is change in velocity, which means v2 minus v1 divided by t, and we get mass divided by t, v2 minus v1. So this is just a rearrangement of the terms, and we know mass is density times volume. So density times volume divided by T times V2 minus V1, and that is density times discharge times V2 minus V1. Okay, so if we add all the forces, external forces, that should be equal to rho times Q times V2 minus V1. Now we know this is the how to resolve the forces. So you have this acting force F, and if you want to resolve the force in y direction, we use this angle theta, which is F sine theta vertical, and if we want to resolve the force in x direction, that will be F cos theta. To analyze the force, we always need to take a control volume. So it is like making a free body diagram in statics. You cut a section where there is a potential change in momentum. So you cut a section here because you know there is change in momentum. If it is a straight line, then there is no change in the momentum. Okay, so when there is a change in potential change in momentum, you cut a section and make a free body diagram of that area, of that control volume of water, and you apply all the external forces acting on that control volume. So on this control volume, what are the acting forces? Weight of water, pressure, and support forces. These are the acting forces. If the pipe section is on a horizontal plane, the weight component is 0. Otherwise, there will be weight component. Now, applying the concept of control volume, the algebraic sum of the external forces acting on the fluid in the control volume in a given direction means either in x direction or y direction, because we always resolve either in x or y direction, that should be equal to the rate of change of momentum in that direction. Okay, so when you talk about the algebraic sum of forces in x direction, that should be equal to rate of change of momentum in that x direction. Similarly, the algebraic sum of forces in y direction should be equal to rate of change of momentum in y direction. Now let's see an example here in a horizontal plane. Acting forces are pressure at section 1. So what are we draw a control volume, and what are the acting forces? So this is the acting force, that is the pressure, because when water flows there is a pressure, that's the acting force. And similarly at this. So it is important to remember the direction of force. We apply the force towards the control volume, apply the pressure from the outside on the control volume, which means at this section the water from this side is applying pressure this way, and similarly from on this side the water from this side applies pressure in that direction. Okay, so that's why the direction should be from the external pressure on the control volume. So this is P1A1, this is P2A2 forces. Now, if it is a horizontal plane, the weight component is 0. So the sum of the forces acting in x direction is P1A1 minus P2A2 cos theta times FRX, right? So we assume the x and y coordinates and we assume this as the theta. So what are the acting forces? P1A1, which is acting on x direction. So there is no need to resolve the force. And this force, the pressure, you need to resolve in x direction, right? So you need to resolve this force P2A2 in x direction, which means P2A2 cos theta, and that obviously direction is this side, that's why it is negative, minus what is the external force acting here? The resistance or the support from the pipe wall. Okay, that's the another force. Okay, so what are the acting forces? The pressure force at two ends and the support force. Okay, so P1A1 minus P2A2 cos theta minus x component of the resultant, which is FRX. Similarly, resolving all the forces in y direction, P1A1 times sine 0 because there is no vertical component of P1A1 minus P2A2 sine theta. Why negative here? Because the force is acting here and the resolution of this force, the pressure force in y direction will be downward, and that's why negative, plus Fry, which is upward, that's why positive. Now this should be equal to the change in momentum. Okay, so how do we calculate the change in momentum? So rho times q times v. Okay, so in x direction, rho. Now how we assume the signs of q and v is very simple. For discharge, inflow in the control volume is negative and outflow is positive. Okay, inflow is negative, outflow is positive. So here rho at this section, this is the inflow, right? So rho minus q times v1, and at this section this is outflow, so rho positive q plus v2 cos theta, right? So you need to have this horizontal component, which is v2 cos theta. Okay, so q is outflow, that's why positive, whereas velocity component is based on its own direction. Okay, so v2 is this direction, so v2 cos theta. Similarly for y, we apply the same concept and get this equation. Okay, so we have the acting forces in x, acting forces in y. Similarly, momentum, change in momentum in x and change in momentum in y direction. So once we have, we can solve to find out what is the value of x and y component of the resultant force, and then finally we define what is the resultant force and where it is acting within, that is in terms of the angle with the horizontal, what is the angle. Now when a pipe in a vertical bend, uh, in vertical bend we also need to add the weight component. Other than that it is the same, but in y direction you will have this weight component as well. So in y direction or z direction, which is the vertical direction, then you have when you make the summation of forces, one is this pressure force P2A2 sine theta, and the weight component which is acting downward, so negative, and this reaction which is acting upward, positive, right? Should be equal to rho q times v1 doesn't have particle component, so you just need the uh, v2 component, and you get this again. Once you have fx and fz, you can calculate reaction resultant force, and resultant angle. This is an example with a nozzle. The flow is along one line which is horizontal, right? So the control volume is only horizontal. So if you make a control volume here, this is only horizontal component of forces, right? And also the momentum. So it has only horizontal components. So, and other thing we need to remember is because this is nozzle, as the water is released to atmosphere, the pressure at outlet is zero. So there is no pressure here. So only you have pressure at this section, but here the pressure is zero. And you apply the same concept to derive the equation.